Before we get back into the Navier-Stokes equations, we need to remind ourselves of some basic ideas about partial differential equations and then index notation. This little segment in the class is a very quick reminder of important parts of partial differential equations. It's probably good to know that the physical laws of the universe can be written, or most of them were being developed today and in the past, are written as partial differential equations. So my view is that if you don't understand partial differential equations, it's probably not possible to understand the mechanics of the universe and how well things really work. A partial differential equation is a differential equation that contains unknown multivariable functions and their partial derivatives. In the context of this class, that might be like velocities, densities, pressures, and their particular derivatives with respect to their dependent and independent variables. The Cauchy theorem states that the Cauchy problem for any partial differential equation, or PDE, whose coefficients are analytic in the unknown function and its derivatives, will have a locally unique analytic solution. And it's definitely arguable if the Navier-Stokes equations have unique solutions or not, or even if they exist, which is some things we'll be talking about a lot in this class. Boundary value problems are going to be involving these partial differential equations with particular conditions set at the walls or boundaries of the fluid. Or we'll also look at initial value problems where the initial conditions, that is the initial state of the fluid, is known. Let's look at some basic PDE. So this is just from a basic PDE class to remind you of notation of the different types of boundary conditions we might be applying to the Navier-Stokes equations. First is directly, which might just prescribe the state of the fluid, like if our unknown function is y and the boundary value has a value of f, what would be the state? So if we have a domain, the unknown might be y, and the boundaries are f. Just for now, f might be like a prescribed pressure or no-slip condition. If the derivative of the unknown variable, y, with respect to the normal direction of the wall or boundary, is f, we call this a von Neumann condition, named after John von Neumann. Then if you take the directly boundary condition and the von Neumann condition, you combine them. Say a coefficient c naught times y, the unknown, plus c1 times the partial derivative of y with respect to a particular direction, maybe it's the normal, that would go as f, the boundary condition at the wall. So it's a mixed. Robin is the combination of the first two. Another mixed type of condition might be y equals f for c naught and y plus c1 of partial y, partial n of f. So there's a little subtlety between them. Finally, a variation of these is the Cauchy one, where y is f and say c naught partial y partial n is g. So notice these coefficients are matched with the original pairings of the Dirac-Leigh and von Neumann condition in these first three additions. So look at this for a second. It's very subtle but important. Dirac-Leigh, von Neumann, Robin, mixed, and Cauchy. Some quick notation. Typically in the first calculus classes, we learn that we write things as say d dx of say u. That's a very typical thing. Partial derivatives use this operator here. It's partial term, partial u, partial x. They're very similar. It physically means here that we're taking the derivative of u, the velocity u, the component, in the x direction. Another example might be partial t, partial y. This means we're taking the derivative of the static temperature in the y direction. Or say partial p, partial z. This is the derivative, partial derivative of static pressure in the z direction of the flow. The 2's here indicate the second derivative of u in the x direction. And down here there's a mixed partial derivative example where we do the partial of u with respect, and then the partial of partial x in the y direction. So this is written so that first you take the partial derivative of u in the x direction, you take that result and apply partial y of partial u partial x. This physically means how the change of velocity in the x direction is changing as we go in the y direction. And we see these mixed partial derivatives in the Navier-Stokes equations. This is a lot to write on the right-hand side, and so we use a shorthand notation of u sub x, uxx, uxy, etc. For example, ux is partial u partial x, uxx is the second derivative of u with respect to x, and uxy is the partial derivative of x and then with y. You'll notice the order that we write these is a little bit different. On the right, we say, hey, partial 2u, partial y, partial x. That means we take the derivative with respect to x first, then y. In the notation, it's left to right, typically, that we'd take the partial derivative with respect to x, and then we take the partial derivative with respect to y. So u, x, y. As an example, what would say p yz be? This would be the partial derivative with respect to y, and then the z, respectively, in this compact notation. So you'll see a lot of people working in PDE writing things more this way because it's a lot less writing than the way on the right. A little bit more about PDE notation. Let's look at the so-called Eulerian notation. The right-hand side is very much the same. We're doing second partial derivatives with respect to f in the x and y directions and all the combinations. We left out z just for simplicity, but there'd just be more components. On the left, another shorthand notation would be right, indicating partial derivative. A second partial derivative, 2 subscript s, or excuse me, on f. So we could also say partial y x q for heat transfer or something. That would be what? The partial q partial y, partial z. Once again, just be careful about the order of operations. We can also write it in this combination, which you'll see too, that we might just raise derivatives to the n power. And be careful, sometimes this could also mean material derivative later. But typically in the class we'll use this notation because it's the most common, I think most compact and understandable.